Welcome to today's Explainer. Right now, deep inside AI hardware, we are witnessing a massive paradigm shift. We're not just talking about incremental speed boosts anymore. The very foundation of how we build these architectures is being completely shaken up. Today, we're going to deconstruct a fascinating evolution, how NAND, a technology we traditionally thought of as just cheap, slow storage, is staging an absolute rebellion to become AI's next critical memory layer. Let's dive in. Right off the bat, we need to address a wildly distorted situation in the industry. Our AI models are generating massive amounts of data weights, but the high bandwidth memory, or HBM bucket, is tiny. It is literally overflowing. Think about this. If you pull apart a modern server rack, the actual HBM capacity being utilized is often just around 10%. Data center operators are dropping millions on state-of-the-art GPUs, but they aren't even buying them for that incredible compute power anymore. They're forced to buy these incredibly expensive chips just to access the attached memory space. We are swimming in compute, but we are absolutely starving for memory.
Here is our roadmap for today. First, the AI memory bottleneck. 2, the new 3-tier memory layer. 3, the magic of hiding latency. 4, the clash of Hynix and Samsung. 5, physical barriers to overcome. And finally, the future landscape of AI hardware.
Let's jump straight into Section 1, the AI memory bottleneck. The current setup in data centers is basically like watching gears grind and break. You have this small, incredibly durable gear, the GPU's compute power, trying to mesh with a massive, trillion-parameter gear of model weights. It's just not fitting. Operators are literally forced to waste a $30,000 GPU purely because they need a place to park data. That expensive compute power sits idle, completely underutilized, causing a massive distortion in the total cost of ownership. If we look back at the timeline, the industry used to be completely obsessed with teraflops. It was all about raw GPU compute speed. But today, because of these severe HBM bottlenecks, we are just recklessly wasting GPUs and generating insane amounts of heat. The critical pivot we are making right now is shifting toward right-sizing the hardware cluster. The future is all about becoming memory optimized by bringing in new memory tiers like HBF and Grand NAND. Which brings us to Section 2, the new 3-tier memory layer. Okay, so how do we actually fix this structurally? The future AI architecture is formalized into a brilliant 3-tier pyramid. At the very top, you have HBM. Think of this as your active workbench. It has near-zero latency, you can access it byte by byte, but the space is extremely tight. At the very bottom, you have your traditional SSDs. That's your distant archive for cold storage. But the real game changer is this new middle layer. We're calling it the nearby warehouse. This is the new HBF and Grand NAND zone, a massive holding area where you can stack mountains of AI weight data right next to the GPU. But how do you actually pull a massive storage warehouse physically close to the GPU? Enter UCIe. This is a universal chiplet interconnect that basically acts as a superhighway bridge. It crosses the vast chasm of the motherboard and physically pulls massive storage capacity directly into the compute package. Thanks to this connection, the compute chip and the heavy-duty NAND memory become one cohesive unit, transferring data at breathtaking speeds. Section 3. The magic of hiding latency. Now, you might be wondering, NAND is inherently slow, right? So how on earth does it function like high-speed memory? It's all about how you move the data. HBM is like a bullet train. It fetches a tiny 1-byte payload instantly. HBF, on the other hand, is like a massive army. It might take a split second longer to start moving, but when it does, it hauls an entire page of data all at once. Because AI weights are read sequentially, meaning they're highly predictable, HBF can simply prefetch the data. By leveraging this sheer volume and predicting what's next, it completely hides NAND's initial slow response time. It's practically magic. And the unsung hero orchestrating this entire illusion is the base die, sitting right at the bottom of the raw NAND stack. This intelligent layer is working overtime. It manages bad blocks, corrects errors in real time, and predicts the data flow. Essentially, the base die tricks the GPU into seeing a flawless, ultra-fast memory pool, completely masking the fact that it's dealing with raw, error-prone NAND underneath. Section 4. The clash of Hynix and Samsung. Let's shift our focus to the corporate battlefield, because South Korea's memory giants are looking at this exact same problem and taking diametrically opposed paths. It's like a highway splitting in two. On one side, you have SK Hynix, partnering up with SanDisk, steering toward an open ecosystem philosophy. On the other side, Samsung is doubling down on a custom integration approach, aiming for extreme performance inside closed loops. When you compare their architectures side by side, the divergence is striking. SK Hynix's HBF is all about massive capacity. They are stacking NAND 16 layers high to get a whopping 512 gigabytes of density, offering up to 3 terabytes per second of theoretical bandwidth, all built on open OCP standards to connect with accelerators like Google's TPU. Samsung's zNAND? Oh, they only care about speed. They keep it low, 4 to 8 stacks, using an SLC mode that only writes 1 bit at a time. The bandwidth is lower, around 200 to 400 gigabytes per second, but because it's deeply fused with an NPU in a closed system, the reaction time is absolutely blistering.
So what does this strategic split actually mean for the market? Well, Hynix is building for massive scale. Their high-capacity parallel processing approach is laser-targeted at giant cloud data centers and open hardware ecosystems. Samsung, however, is aiming its ultra-fast, tightly integrated architecture straight at edge AI. Think robotics, mobile devices, and highly specialized custom accelerators, where instant response time is literally make or break.
Section 5. Physical barriers to overcome. Of course, no engineering miracle comes for free, and the physics here are hostile. When you put memory right next to a GPU, you are parking it next to a blazing furnace. NAND stores data using trapped electrical charges, and extreme heat literally causes that charge to leak, ruining data retention. But an even bigger threat is the write penalty. Unlike model weights, which are read-only, context data, the KV cache, has to be constantly rewritten. Because NAND requires you to erase entire blocks just to overwrite data, this constant churning destroys NAND cells shockingly fast. And that hostile environment leads us to a massive commercial risk. We are talking about a non-serviceable architecture. These chips are permanently bonded together via UCEE on a single substrate. If just one single NAND component suffers a thermal failure, you can't just swap it out. The entire package, a piece of hardware that might cost over $10,000, instantly becomes unrecoverable e-waste. That is a staggering financial risk for anyone deploying these systems at scale. Finally, Section 6, the future landscape of AI hardware. I want to emphasize something absolutely crucial here. The ultimate goal of all this isn't just to use cheaper memory. It's about putting the entire infrastructure on a diet. Think about it. Instead of needing 8 GPUs just to hold a model's footprint, this new near-compute NAND lets you do the exact same job with just 4 GPUs. You literally shrink your physical server footprint in half. You drastically reduce those extreme cooling requirements, and you cut out massive networking switch costs. That compounding reduction in total cost of ownership is the real reason data centers are willing to stomach the physical risks we just talked about. So, how does this map out the future? The hardware landscape is fracturing based on workload scale and ecosystem openness. The massive hyperscale clouds running giant model inference, they are standardizing right around SK Hynix and its open standard HBF. Meanwhile, the specialized, highly responsive sectors like robotics and autonomous driving, they will be dominated by Samsung's vertically integrated zNAND-O. It is fascinating that 2 memory giants from South Korea are essentially holding the steering wheel for the entire global AI hardware paradigm. I want to leave you with a provocative question to wrap up today's explainer. For years, the AI revolution has been led by the masters of compute, the companies building faster and more powerful processing engines. But as we've seen today, the true physical limits of artificial intelligence, the actual bottlenecks, are now being dictated and solved by the architects of memory. So as we look at this next era of the AI hardware race, who truly wins? Is it the masters of compute or the architects of memory? I'll leave that for you to decide. Thanks so much for joining us on this deep dive, and we'll catch you next time.